let's get started. So a couple of things. There were a couple of typos in homework, and hopefully everybody got the email correcting them. If not, the current version of the PDF on the website is correct. So that should be it. Then last time we talked about this idea of computing integral homology via matrix reduction. Right? So what is the procedure? Let's just remind ourselves of what's going on. So you start with a simplicial complex like always, and then you want to compute let's say the n homology of K. Correct? So, right, so what do you do? So starting at Cn, so this is the sort of the place where most of the things we want to do happen. So from here, we map out to the Cn-1 chains, and then we continue, and then we map into Cn plus 1 Kz using delta n plus 1. And this continues this way. Okay, so this is where the action is going to happen. So here, let's say that we have our bases, say, tau 1, tau 2. Today I'm going to use MATLAB indexing just to annoy the Python purists. And maybe here I have a basis sigma 1, sigma 2 through sigma, let me get the indices right, sigma m. And here perhaps I have a basis u1, u2, all the way to ul. Okay? So usually these bases, we take them to be just the standard simplices. So these are the n simplices, these are the n plus 1 simplices, and these are the n minus 1 simplices. The first step is to set up the matrix representation. So set up matrix representation. So throughout the computation, we maintain two matrices. We maintain the matrix for delta n plus 1, which is given in basis elements in terms of sigmas and taus. So I have a sigma 1, sigma 2, all the way up to sigma n. And here I have tau 1, tau 2, all the way up to tau sigma m and tau n. And the other matrix I'm maintaining is the delta n matrix. And then that goes from the taus to the u's. Okay? So we set up the matrix representation. And essentially what we do is in each column, we put the boundary of each one of these elements in terms of these guys over here. The second step is we do sort of elementary row column operations to reduce delta n, right? And not only that, we're going to take also all the column operations we did, and we're going to replicate whatever the inverse is to the rows of delta n plus 1. So turn column operations for delta n into row operations for delta n plus 1. So we mimic, so whatever we do here in the columns, we do the inverses here in the rows, so that whatever change of basis we're doing here is maintained in here. And we do that simultaneously. So the result, once we're done with it, is going to be two reduced matrices.
So if we do this, if we have a matrix, say, okay, so let's just say we're multiplying on the right by matrix A.
Yeah.
Delta n.
Yeah.
Is it multiplying on
by
the
the
side?
inverse?
Okay, inverse. Okay.
Yeah, correct. So, right, so we get that, so we get new matrices, right? So new matrices. Right, so here, since we didn't touch the columns, in here, the columns look the same. So, when we just sigma m. And then here, I did both row and column operations. So that's going to give you a new set of bases, which I'm going to denote with tildes. And this is going to go all the way up to t tau n minus z. And then here I have u0, so another, so u1, here let's say n minus z, tilde n minus z plus 1, u tilde l, and then here I continue with tau n minus z plus 1, all the way up to tau n. And then the reason why I wrote it in this fashion is because in here we're going to have our usual matrices. And here I have so K1, K2, K minus Z. And here K1 divides those two, divides K minus Z. And these guys that I have over here, let's call them sigma 1 all the way up to sigma z, are going to be the cycles. So since we're doing the operations simultaneously between columns and rows, then here I'm going to get the same bases I got in here. So you get some tau 1 tilde all the way up to tau n minus z. Here we get tau n minus z plus 1. And over here. Cool. You know what? I'm going to change these for the zetas. Okay, so zeta 1 for zeta z. And here's the thing to notice. Right. So, so notice that these taus that I have here, tau 1 tilde, tau tilde 1, all the way up to tau tilde nz, when I apply delta n to them, I get things that are not zero. Correct? So that means that they cannot get hit by delta n plus 1. In other words, this is actually 0, and here we just get stop. Okay? So that's the first observation. The second observation is that these guys right here So these give the columns, right? So this gives you a basis for Zn. Okay? These guys right here give you a basis for Bn minus 1. Right? Because I'm looking at the image of delta n. So the image is going to look like K1, U1 tilde, K2, U2 tilde, all the way up to KNZ, UNZ tilde. So this accounts for all the boundaries in dimension n minus 1, because I'm taking the nth boundary here. What else can I say here? So perhaps the thing to say, and this is a detail that we're going to hopefully remember in a minute, is the following. If you look at n, right, sort of the number of columns I have in this matrix. So what is n? N is going to be exactly the same as the number of n simplices I have in the complex. So this is the number of n simplices. Right? That's the first observation, because, again, we started with the basis of n simplices, so that has size n. Okay? That's the first statement. So the number of n simplices is going to be what? It's going to be n minus z plus z, right? So it's going to be n minus z. So n minus z plus z. And this guy right here is what? Is the size of Bn minus 1. Then this guy right here is the size of Zn. Cool? So if you remember your linear algebra class, this is the rank nullity theorem that says that the size of the domain can be split into the size of the image plus the size of the kernel. Right? So rank nullity from linear algebra. So hopefully we'll be able to remember this relation between the number of n simplices, the size of the boundaries, and the size of the kernel. I wonder if you'll be able to remember it. I should just write it somewhere else. Let me write it here. So this is the dimension of Bn minus 1 plus the dimension of Zn. Okay? Okay, cool. Then the next step, so step 1, step 2, now step 3, is we're going to do some more row column operations, but to the matrix I called stuff. Right, so step 3, so reduce stuff. So what that does is you start from something that looks like this, zeta 1 all the way up to zeta z. And here you have your sigmas. Sigma 1 up to sigma n. Sigma m. So once we reduce it, we're going to get something that looks like, perhaps I'm going to get some other sigmas. So sigma tilde 1 all the way up to sigma tilde z minus b. We get z minus b plus 1 all the way up to tilde z. So that's going to be the basis I get in the rows. And in the columns, I'm going to get some new guys. So perhaps I'm going to call them, so from here to the new bases. So perhaps these are some sigma tilde all the way up to sigma tilde z minus b, sigma tilde z minus b plus 1, and all the way up to sigma tilde m. Right? So that's going to be the new matrix that I'm getting once we reduce. So as always, here I'm going to get some n1 all the way up to n z minus b with the usual conditions, and these guys are zeros. Okay? Now, the thing to remember is that this is the size of Zn, right? Question. What are these columns? What is the size that we get there? What is it? So this should be the dimension of Bn, right? So dimension of Bn. Okay. Which is, I guess, the same guy over here. So, step 4, we compute homology. So step 4. So we read off whatever we got here in the computation. So what is that? So we get that a basis for Zn is what? It's going to be all these zetas. So zeta 1 tilde, zeta z minus b tilde, zeta z minus b plus 1 tilde, and then zeta z. So that's a basis for z. So basis for Bn it's going to look like, right, so if you look at the guys in here, so what is the basis? The basis is this guy goes to n1 times that, all the way up to this guy goes to these times that, and everything else is 0. So that means that these products are giving you the basis for the image. So the basis is going to be n1, zeta 1 tilde, n z minus b, zeta z minus b tilde. And when you do, yeah.
Is it all of the zetas on for the basis of Zn?
Yes, yes. So let's get back to it. So, I erased it already. So
that's the image?
So the zetas are the cycles, the kernels, right? So
some of them are not cycles, right? Some of them,
all of them are cycles. What happens is that some of these guys are not boundaries.
mm-hmm.
All of them are cycles. Remember that every boundary is also a cycle because delta squared is 0.
Right. No, that clarifies it for me.
Okay, cool. So now when we compute homology, we do Zn modded by Bn. And that is essentially modding this guy by that guy, these by that, and the ones that are left over do not interact between them. In other words, this guy here is going to give you what? It's going to give you Z mod N1Z all the way up to this guy, which is going to give you Z mod N Z minus B Z. And all these guys that do not have anything that is modding them by, you're going to get Z's here. And how many of them? You're going to get B of them. Okay. So that's the homology algorithm. You set up everything like matrices, reduce very carefully, and at the end, when you have the matrix set up as cycles in n+1 simplices, then after a Smith normal form computation, these guys over here give you exactly the coefficients in this piece, and then the rest, the leftover b's, right, meaning these guys, the leftover cycles, there is b of them, are going to give you the number of times that z appears in here. Okay? So that is the algorithms. These guys have names. So this is often called the torsion part. And this is called the free part. So there are reasons for these names. Yes, go ahead.
So you just said the names, the torsion part.
Mm-hmm.
Are those, if you had it arising from an orientable manifold, would you not have a torsion part?
Nope. Nope. I mean, the reason, so I guess the best way to think about the torsion part and the free part is with the examples that we had from before. So, for example, if you compute the homology, let's say in dimension 1 of the circle, let's put as, so then this gives you something that is just z, and it represents the one-dimensional hole that the circle has. If you compute h1 of RP2, we did this last time, right? So now what does this look like? So this looks like a disk with boundary points identified, correct? So the idea was that if you go from A to A following this curve, then this gives you a loop because you start at A and end at A. So this is an actual cycle. But then the idea is that if you go from A to A and then you do it again from A to A, then you're taking your cycle, let's call it gamma, and you're saying that going around it twice is 0, because this curve that I have here is filled in by this solid disk, right? So I guess this is weird to say it out loud, but what's happening is that you have this loop that when you go around it twice gets filled in. And that's why this is, or at least the intuition as to why this is z mod to z, which is, that is the class of 0 and the class of gamma. So the free part of homology is indicating loops that look like circles or spheres of the appropriate dimension. And then the torsion part is indicating cycles that you go, when you go around them, let's say n1 times, then they get filled in. It's similar to this RP2 picture that we have over here. Again, you know, I've thought about these ideas for a while now, and I still get confused as to how to better explain these ideas. The geometric intuition can be tricky, but hopefully, if you hang on to RP2, that'll be a good example to have in mind. Another example we looked at was the Klein bond. And what we saw is that this looks like Z cross Z mod 2Z. And it's indicative of sort of one circular direction that perhaps looks like this. And then another direction that is projective-like. So to answer your question, if your space doesn't have any weird torsion, like twisted pieces, you shouldn't expect the homology to have anything weird in it, right? So this is an indication of having a complicated space. Okay? Cool. Let me now give you a definition, now that we're here. Where do we do it? You know what? Let me before we do that, let me add one more comment. Notice that the dimension of Z, right, is equal to what? It's equal to Bn. Bn plus B. Where again B is this B. Okay, just by looking at the size of the matrix. Okay. So I'm going to give you a definition, and I'm going to use this side of the board because I don't want to erase these two pieces. So here's my definition. I'm going to do it here. I'm going to define what is called the Betti numbers. So we saw that the first day of class, but now we have the right tools to actually give you the definition. So beta n k, so this is called the nth Betti number of k. Is equal to what? It's going to be equal to the number of z's in the free part. The free part of Hn. Okay. So, what is this? B. Okay. So let me update my formula from here. This is actually equal to the dimension of Bn plus beta n k. Okay. Cool. Okay, so again, the way to think about the Betti numbers is sort of the number of sort of nice, easy, n-dimensional holes in the space. And the torsion part is sort of the complicated part. Okay, okay cool. Okay, so now that I have this formalism, I want to, again, remind you of a definition we had at the beginning. And I can now erase this because all I needed was B from this picture. And now we have it. So let's erase that. By the way, Matthew, here's the comment that I should have made before. When you asked if I have an orientable manifold, do I get torsion? The answer is, if you compute the nth cohomology of the nth homology of an n-dimensional manifold, then that is Z. If and only if orientable. That is the statement, but we don't need anything like that to keep going. I'm going to define now something that we saw again at the beginning. It was the Euler characteristic. So the Euler characteristic chi of a complex, do you guys remember how we did it at the beginning? It was vertices minus edges plus faces. So what do we do now? So we just say minus 1 to the number of n syntheses. Okay. So before we had something that was just two-dimensional, and that's why we only had vertices, edges, and faces. But now we've seen that we can create complexes with a lot of n-dimensional simplices. So we just take the alternating sum of counting them, and that is the Euler characteristic. Okay, okay, cool. Now I'm going to relate the Euler characteristic to the Betti numbers. We also saw that the first day. So here's the theorem. Another way to compute the Euler characteristic is to take the alternating sum of the Betti numbers. And hopefully we can see it here. So I wanna make a comment first of all. So here's the comment. We define the Betti numbers in terms of the homology of a space. That's the first step. So in that sense, homology is bigger than Betti numbers, right? So this contains more information than this, right? In the sense that, how do you compute this guy? You first compute this guy and look at how many z's it has, right? You forget about the torsion. So this is smaller than this. Now, you look at the Euler characteristic, right? And this is something you're computing in terms of the Betti numbers, if this theorem is true, and it is. So this is smaller than the Betti numbers. Smaller in the sense that it has less information, right? You're crashing down a bunch of stuff doing this sum to get your final characteristic. What is cool about it is that it is telling you that something that you compute in terms of just a simple count, like how many vertices, how many edges do I have, is actually related to something that is tricky to compute. Okay? So that's the first statement. Let's see why this is true. Okay. So here's the proof. So I want you to notice that we already did all of the work, actually. So we already showed that if you take the number of n-dimensional simplices, that is exactly the same thing as doing dimension of bn minus 1 plus dimension of zn. Okay? So this is, so we showed that if you compute chi n as sort of, if you count the number of simplices, then this is the same thing as the dimension of bn minus 1 plus the dimension of zn. Okay? That's from here. And we also showed that zn can be computed as the dimension of bn plus the Betti number. So bn minus 1 plus the dimension of bn plus the nth Betti number. Cool. And again, I just substituted this into the z piece. And now the magic of math, right? So things are going to cancel out because this is exactly the same thing as, so I'm going to put this guy over here, so minus 1 n b n k, plus, I'm going to take this guy first, so 0 minus 1 dimension of dn, and next I'm going to take this guy here, so plus sum n0 minus 1 dimension of bn minus 1. Okay? So here's the magic of adding and subtracting the same thing. So if you make, let's say, if you do a substitution, let's say that you make L equal to n plus 1, or to n minus 1. you make that substitution just to change indices. So here you get L. Let's do it here at the bottom. So you get sum minus 1n bnk plus sum 0 infinity minus 1 to the n dimension of the n plus L from minus 1 to infinity minus 1 to the L plus 1 dimension of BL. Okay? Just performing a sort of a straight up substitution of L equals n plus L minus 1. L n minus 1. That's the substitution I did. Okay? But now let's think about for a moment what this guy here is. So when L is equal to minus 1, right? What do I get here? I get B minus 1, correct? What is B minus 1? Is the image of delta 0, right? And that is 0, right? It's the last differential that we have. So, in fact, this is equal to just reindexing from 0. Right? The minus 1 doesn't contribute in any way. So I'm just going to do it here. Boom, 0. And then this plus 1 here, we remove it and turn it into a minus 1. Boom. And now this cancels out with that. Done. So it's just by keeping track of what the dimension of Z is, by literally looking at the matrices, and by looking at so this is rank nullity, and this is the relation between the Betti numbers and Zn and Bn, all by looking at the sizes of the matrices. Okay? Okay, so I want to switch gears a little bit. Yeah, I'm going to give you a final theorem, and then I'm going to show you some applications of these invariants. So in particular, we're going to see some applications of computing Betti numbers for real data, and some applications of that to neuroscience, and then I'm going to show you some applications of these Euler characteristic to problems in computer vision and physics, actually. So cosmology. So that's that. And the thing that I wanted to remember is the relation between the Euler characteristic, the Betti numbers, and how to compute the Euler characteristic. Okay. So before we show the applications, let me give you a final theorem that ties everything together. You know what? Instead of, let me do it on the slides. That's okay. So this was sort of the first image we saw at the beginning of the course. This idea of topology being the place where we think of objects as being equivalent if one can deform one into the other. Now we have hopefully a theoretical notion of deformation, which is that finding F and finding G so that the compositions are homotopic to the appropriate identities. We also saw this theorem of the Euler characteristic, that if you look at only vertices minus edges plus faces, and that was for something two-dimensional, then that this was independent of the triangulation, and invariant under topological deformations. Correct? That was what we saw first. We also computed the Euler characteristic for these spaces. For the circle, the sphere, the torus, the Klein bottle, the projective plane. And right there, we can see that the Euler characteristic can indeed sort of tell the sphere apart from everybody else and projective space apart from everybody else. The question is that, or at least the problem is that the Euler characteristic is not strong enough to distinguish between the Klein bottle, the circle, and the torus. Okay? Now, and I'm going back to what we just wrote. The notion of deformation that we're going to use is this idea of being able to go from left to right and then from right to left in such a way that the compositions are homotopic to the identities. So that's the notion of deformation that we're going to use in this course, and that one usually uses in topology. This is called, when this happens, one says that K and L are homotopy equivalent. That's the name, homotopy equivalent. And what we've proven is that whenever you have two spaces which are homotopy equivalent, then their homologies are equivalent. That implies that their Betti numbers are equivalent. And then that implies that the Euler characteristics are also equivalent. Okay. So that's what we've seen thus far. And it is in that sense that homology is sort of the bigger of the invariants, and the stronger of the three invariants. So going back to the three spaces that were problematic, right? So the Euler characteristic already distinguishes the sphere from everybody else and the projective plane from everybody else. So let's just get rid of them, right? It's okay. Euler characteristic can take care of that. Now we have the same Euler characteristic. So what do? Let's look at their homology, for example. So what we've seen is that the homology of the circle looks in dimension 0 like Z, because there's only one connected component. In dimension 1, you have Z because you have this one circle. And in higher dimensions, you get 0 because there are no higher dimensional information. And now if you compute the homology of the Klein bottle, then you get, in this case, Z cross Z2, and then 0 in 2 dimensions. Okay? So already homology, which is the stronger of the three invariants we've seen, does a good job of distinguishing between this space and that space. So that's a win. Let's look at the homology of the torus. So, no surprise, it is different from the homology of the circle. It has two-dimensional information, and it is different from the homology of the Klein bottle. Right? So this is an invariant that is going to distinguish between all the examples we have in this slide. Just for comparison, let's take a step back and look at the Betti numbers. Okay? So, if you compute the Betti numbers of the circle, then you're counting the number of z's, right? So there's 1 here, so that's why you get 1 in here. There's 1 in here, that's why you get 1 in here. And if you compute the Betti numbers of the torus, you get 1 in here, because there's 1 here, 2, and 1, okay? So the Betti numbers are enough to distinguish between the torus and the circle, right? We didn't have to go all the way to homology to get to distinguish these two spaces. But now if we look at the Klein bottle, notice that the Betti numbers are 1, right? I have a Z here. 1 here, I have another Z. Is the number of Z's, remember that? And then 0. So the thing to notice is that the Klein bottle and the circle have the same Betti numbers, right? So you do have to go all the way to homology to distinguish them. Okay? And just for completeness, let me just put all the other information on the screen. Okay? So this is the sort of balancing act that we play all the time. We have hopefully a bunch of invariants that are powerful, and hopefully you go with the ones that are easy to compute. The easiest to compute is the Euler characteristic, but as we saw, it lacks power, at least for these types of spaces. Betti numbers are easier compute than homology. And sometimes they fall short. Homology is the stronger of the three, but even homology is not enough to distinguish all the spaces we want in topology. But we won't worry about that in this class. So the first application that I wanted to share with you is an application to neuroscience. So this is a BNAS paper from 2015, I believe. Yeah, 2015. And here's the question that they try to answer. They start with something called place fields. What is the idea? They put a rat in an environment, and they make it run through the environment. And they're measuring the spike trains of the neurons in the hippocampus of the rat. Okay? So you can think of these as one neuron, this as time. Each one of these spikes is when the neuron fires, and this is the path that the rat is traveling in the environment. And they can say, for this neuron, these are the sort of places, the locations in the environment where the appropriate neuron fires the most. Does that make sense? So, in a way, the hippocampus has these sort of neurons that are coding for specific locations in the environment. So they act like a GPS, if you will. So they're called place fields. So what is the question that they try to answer in this paper? So they take neurons, from this rat that is moving around this environment, and then for every 2 neurons in the data, they measure the correlation between them, how similar they are. That can be measured by looking at like offsets, like time offsets of one neuron versus the other, and seeing how similar they are. And then through that process, they get this matrix where you have all the neurons in the data, and then for each pair of neurons, you have how correlated they are. Okay? So this is the data. And the question to answer is, how far is this matrix from being random? Okay? How far is this matrix from being random? A secondary question is, if it is not random, is it related in any way to a geometric object? Is there a geometric organization to the neurons in the hippocampus of the rat as it moves around? Yes?
I'm sorry, if it's random, that's saying that there's no correlation between the different neurons firing at different points of the path. Is that what they're trying to say? Or?
Yeah, let's say that, yeah.
Okay.
Yeah.
Well, if it's random, then there's no distinguishing how each mouse is thinking about the maze, right? So.
Yeah, but it's more, a little bit more than that. But that's what I'm going with this.
Oh, okay.
Let's say yes. Okay. So that's the question: random or not random? Are brains organized geometrically, or the wiring and the correlation between the neurons doesn't matter? That's the question. So this is what they do. They say, okay, neural data is pretty noisy, so we're not going to trust the actual measurements of correlation. So what they do is they look at the correlation matrix that we just constructed, say that here you have 5 neurons, and what they do is they turn the actual values into an order sequence by just saying, this value is smaller than this value, and this value is smaller than this value, and so on.
So they just rank the...
Just rank order of the values in the matrix.
So just change it to a non-parametric problem.
Exactly. And then but the cool thing is that now the final matrix of orders is invariant under sort of, how do I say it? Increasing parameterizations of the problem. You see what I mean? Like if you pass through a nonlinearity, like a sigmoid function that is increasing, then the order is going to stay the same. Okay? So you're constructing something that's invariant under monotonically increasing reparameterizations. Okay? So given now this representation, they construct something they call the order complex, which is nothing but the Ribbs complex applied to this matrix. Okay, so they take the Ribbs complex on this matrix. Of course, they have bigger matrices in the data, and then they count how many edges I have. This is the density of edges in each complex. Okay, And you see that as I increase the scale, I am collecting more and more things. We saw that with the Rips complex before. Okay? And here they're showing...
So they're just increasing alpha.
Just increasing alpha, exactly. That's exactly what they're doing. And here you can see sort of cycles that are forming. And this is a little bit harder to see, but this is a two-dimensional sphere in the complex. At any rate, what they do then is they compute the Betti numbers at each scale. Okay? And this is the curve, these are the curves that emerge. So this would be Betti 1 in terms of this density of edges, right? So the more edges you have, the farther to the right you're going to be. Yes?
How many points were they calculating in this particular correlation graph? Because
Yeah, I don't remember. I think it was between like 1,000 or 10,000.
How long did this take to compute?
I don't know.
Computing Betti 2, maybe.
Mm-hmm.
Betti 3
Sounds difficult. Yeah, no, that's a good question. I don't know how hard this was computationally, but they did it.
Yeah.
They did it.
Computer to do it.
So these are the Betti curves for this type of data of construction. And this is for randomly generated matrices. So this is how randomness looks like. There's actually a very cool paper analyzing theoretically these Betti curves for random complexes. That is a big area in applied topological random topology. Okay, at any rate, if this is random, this is what actual data looks like. So this is how maths look like. And what they saw is that when they compare the data versus a model that takes into account geometry, they get Betti curves that are that are more similar to the data than those generated through random models. And these are models that are sort of attuned to the data that they have. Right? So they used these analyses to say, look, the patterns of correlation in place cells are more geometric than random. Those are the upshot. And then, but if you think about the question, how do you measure randomness in these types of measurements? It's non-trivial. What are the things that you have to compute about them? Okay. So I thought this was a very cool application of a simple, not simple, of an elegant idea. The next application is from computer science and sort of machine learning and computational geometry. And it's from this paper, I think it's 2014. So this is efficient classification or using the Euler Characteristic. So now, instead of Betti numbers, they're going to compute the Euler Characteristic, which is simpler to compute, right? It's just counting simplicity, edges, faces, and so on. So what do they do? So they take let's say that they take a data set, like the Tosca data set. So it is comprised of objects that look like the cat on the left-hand side. This looks like a smooth surface, but it's actually a very dense mesh, a very dense triangular mesh. Okay. So then for each point, for each vertex in the mesh, they compute a discrete version of curvature, and that is the colors that you're seeing. So regions in red are more curved, and regions in blue are more flat. Okay. So they use curvature as a function of the vertices, and then say, you know, give me all the regions in the mesh that have values above a certain threshold. For example, in this case, 0.05. And that is all the things in red. Okay? And then what they say is, give me the Euler characteristic of the region in red.
This is plus or minus 0.05 curvature?
No, these are all the things that are above 0.05.
So only positive curvature.
Oh no, the curvature can also be negative. So between -1 and 1. That's the range. Okay, so they compute Euler characteristic for each threshold value, and that gives you, if you think about it, an Euler curve. Right? So for each value of the threshold, you're getting a value of the Euler characteristic for the things above that threshold value. Here's another, oh, and here are the Euler curves for different animal meshes. So if you look at cats, these are all the black curves. And again, for each value of the curvature, you're looking at the Euler characteristic of the red region. Okay? And what they did was a simple SVM, supported vector machines classifier, to classify the dogs, cats, horses, and Michael. Michael is a person. It could be a cat too. I think it's a person. They also applied this idea to 3D scanned stones. So same idea. This is a big 3D mesh. Compute curvature at each point, and then look at the Euler characteristic of the things in red. So everything that's above a certain threshold in curvature. And these are some of the results they got in classification accuracy for those two data sets that I just described. So you get using different functions. So I mentioned curvature here, but they have other ways of measuring shape locally, and the results are reasonable. Right? Okay, cool.
Were they classifying just 3D objects?
Yeah.
And then how many 3D objects?
I think it's like 70 objects.
70. Okay.
Yeah, it's not that. It's not a big. It's not a big collection of data sets, but each object is big, right? Like the meshes are large. Yeah.
Does that depend on how in 3D the object be oriented?
Oh, that's a good question. That's a good question. So the question would be: does the Euler curve depend on the pose of the object? What do you guys think?
Yes.
Yes.
The answer would be no.
Oh, well, yeah, because it would be.
I mean, if you're doing,
it's invariant.
it depends. It depends. The answer is probably no. Let me say why. If you're using curvature to sort of say, give me this region, right? Give me these regions with this high curvature. Curvature does depend on your position, right? If you're like this, then this area is flat, so the curvature is near zero. But if you change it, then this curvature is going to change. So the regions that you're computing Euler characteristic of change. Therefore, the curve is going to change. However, if you used a different function that didn't depend on the position, then the Euler characteristic wouldn't either. Does that make sense? So it's the function that because the Euler characteristic is counting vertices minus edges plus faces, right? So the only thing that matters is what vertices, what edges, and what faces are included in the count. And that's where the position comes in.
So depends on what. Okay.
It depends on the function that you used to select the red region. Correct? So if it's a function that doesn't depend on the position, the Euler characteristic won't depend on the position.
So then, what about had something called like shape index?
Yeah, I remember what that was. Shape index, and it's one of the best classifiers. But it's not that different from curvature, at least for the cats. This is out of the rocks.
So something like distance from center would not change.
It depends on how you measure distance, though. Do you measure it along the shape? Then I would say yes.
How
Out
about
of the center, though.
now that choose the specific part, choose the whole object?
Mm-hmm.
What the result will that be? So
If you choose what?
the whole object, 3D object, and not
Yeah.
like use a function to select some positions.
Okay.
All the positions.
Yeah. So if you do that, you get the number that is here, right? Because this is saying, give me all the values that are above this threshold, and compute the Euler characteristic for that. So this will be the Euler characteristic of the object, right? So this value is independent of the position, for example. What's that?
Nothing.
And then the final application is to cosmology. So this is about microwave background radiation. So how the story goes is that after the Big Bang, the universe was hot and steamy and uniformly, and more or less uniform. And then as time goes on, the pattern diffuses. And what we observe today, or at least the hypothesis is that the radiation that is left over from that process serves as a sort of, how do I say it? As a, not confirmation, but as a, what's that?
Remnant?
No, I mean, it is a remnant, but it's used as a strong argument toward the Big Bang as the right theory. Evidence, yeah, strong evidence, that's the right word. So they do exactly the same thing as with the cats that we saw before, right? So they take, by the way, these data this is 3 years worth of data and millions of dollars in pre-processing and just getting this picture. So what they did was they took let me show you the final picture. So the dots are the data, and they computed the Euler characteristic. Those are the dots for values above a certain threshold, like they did before. Okay, the curve is the fit, the best fit from a particular set of initial conditions for the universe. And in particular, it's a Gaussian random field. It's isotropic. So they evolve the field, compute the Euler characteristic, and then see how well they did. This is done actually analytically because one has solutions. At any rate, the fit is pretty good, right? So people say, of course, the universe was random Gaussian to begin with. And then the thing, it's interesting how physicists look at the world. So they look at this, and they say, oh, there's new physics around nu equals 1. So there are more measurements that need to be done to actually find the known Gaussian nature around these values. Okay, so it's not that the fit is a little bit wrong, and we can live with it. No, they say we need to measure more around this, which is cool. At any rate, so these were 3 applications of the Euler characteristic and the Betti numbers to sort of measure shapes of objects and use that in things like classification and analysis. So what we'll do on Wednesday is we're going to jump into linear algebra. So we're going to change Z. We've been doing everything over the integers. All the matrix reduction over the integers. We're going to change that for a field. So we're going to do things like rational numbers, or real numbers, or Z mod P for P prime. And then the algebra is going to get a little bit easier, but it's going to allow us to compute something called persistent homology, which in a way is able to compute the homology for a whole family of complexes all at once. I'll tell you more about it on Wednesday. Okay, that's it.